Hello, and welcome to a lecture on the uniform geometrical theory of diffraction. I'm Steve Ellingson. So first, let's reacquaint ourselves with what's been going on previous to this lecture. In a previous lecture, we introduced the geometrical theory of diffraction, or GTD, as a means to compute diffraction from edges in perfectly conducting surfaces. The example I provided in that previous lecture was diffraction from a half plane, and the application of this whole business is diffraction from the rim of a large reflector, and so that we could determine the far side lobes, which we really don't have another technique available. Unfortunately, GTD fails at shadow boundaries, that is, in discontinuities in the geo field. There is a geo incident field and a geo reflected field, and they suddenly turn on and turn off at these shadow boundaries, leaving a discontinuity. Unfortunately, GTD doesn't address those discontinuities, and in fact it predicts an infinite field at those locations. So in this lecture we'll explain the uniform geometrical theory of diffraction, and we'll show a few other things as well. We'll show how GTD can be used to compute diffraction from wedges, not just edges, and how UTD can be used to determine the diffraction from curved wedges. Okay, an overview of this lecture. First, I'll remind you about the GTD diffraction formulation. We'll introduce wedge diffraction geometry. So we're extending the problem to that of wedges, not just simple edges. And then we'll extend GTD to wedges. I'll introduce the UTD diffraction coefficients, and then we'll return to this example that we previously addressed, that is, diffraction from a straight edge in a perfectly conducting half plane. And just note that aside from the relevance of this kind of problem generally, it's also a not bad approximation for diffraction from the rim of an electrically large paraboloidal reflector. In other words, if the reflector is big enough, we can model the diffraction from the edge as being from a straight edge in a perfectly conducting half plane. That's something we'll return to in a later lecture. Okay, so here's your reminder on GTD edge diffraction. The way you do it is you find all the points of diffraction using the law of edge diffraction, or Fermat's principle, whichever you prefer, whichever is most convenient. But you identify the discrete number of points for which we anticipate a GTD contribution. And then for each of these points, which are also stationary phase points, we get one contribution, and it's computed as shown here. And again, this formulation is explained in a previous lecture, so I'm not going to repeat a detailed discussion of this. I'll simply point out that we have some contribution from the incident field multiplied by a diffraction coefficient, d sub s or d sub h. We have a spread factor, which is in the geometrical optics form, and we have a phase factor, which is in the geometrical optics form, so that the GTD field turns out to be a geometrical optics field. And really the diffraction comes in through this computation shown here. Here's how to compute rho super c needed in the spread factor. And note the diffraction coefficients should depend on the surface geometry at the point of diffraction, and the direction of incidence, and the direction of diffraction, that is the direction which the diffracted ray travels. Now the only difference between UTD and GTD turns out to be here. Everything else is the same. Here, again as a reminder, are the GTD diffraction coefficients, also sometimes referred to as the Keller Coefficients, after the author of the paper where these were first described. These are provided simply as a reminder. Okay, wedge diffraction geometry. So we're going to consider a more complicated range of problems, that is wedges. Now an edge is simply, for example, here's a sheet, right? This surface here, this line, is an edge. But now we're considering more complicated things. For example, wedges, where perhaps we have an edge here, but it is formed by the intersection of two surfaces. And perhaps these two surfaces are curved, as shown in this diagram down here. So what I'm doing in this slide is providing the variables that we use to define this particular class of problems. So first, we have this thing WA. WA is the wedge angle, For a simple edge, like here, it's simply 0. The wedge angle is 0. If the wedge angle is greater than 0, then we have this situation as shown here, and also as shown in the diagram down here. Now, you recall seeing a parameter n in the GTD diffraction coefficient formulation, and I said that n equals 2 for a simple edge, or for a simple rim if we're talking about reflector antennas. In general, n is computed from the wedge angle, and the relationship is this one, n equals 2 minus the wedge angle in radians divided by pi. So you see if the wedge angle is 0, we end up with 2. If the wedge angle is pi, then we end up with 1, n equals 1. Now you might find that interesting because if the wedge angle is pi, then there really is no edge. It's simply all a flat sheet. And you wouldn't expect any diffraction. But I think if you enter n equals 1 in the GTD diffraction coefficients, you should find that, in fact, the diffraction coefficients are 0 as expected. So this should all make sense as you try it out. Now also we identify these things called the 0 face and the n face. The 0 face is the face which is most directly illuminated by the source point. The n face then is the other face. We have these angles phi super I measured from the 0 face to the direction of incidence, and phi super d measured from the 0 face to the direction of diffraction. So these angles are always measured with respect to the 0 face. Also, because we have two faces to make this wedge, we have two surface normals at the edge. There is a surface normal n hat sub naught, which is perpendicular to the O face, or the 0 face, and we have n hat sub n, which is perpendicular to the n face. So we have two surface normals there because we have two edges, and there's a discontinuity in the curvature at the point where the edge exists, q sub d, so we have two surface normals. And these turn up at various places in the diffraction coefficients. Here is the UTD curved edge diffraction coefficients. So these are the coefficients you can use to replace the GTD diffraction coefficients to get these benefits I've been talking about. By the way, these appear in this very famous paper by Quimjian and Pathak, 1974, a uniform geometrical theory for diffraction of an edge in a perfectly conducting surface. And this paper talks about these diffraction coefficients, as well as talking about a whole bunch of issues related to ray optics, including geometrical optics from curved surfaces and so on. So a very important seminal paper, in fact, in this field. The form of the diffraction coefficients is 4 terms, these 4 things here. Each term is the product of a cotangent function of the angles of incidence and diffraction measured in the plane perpendicular to the edge tangent, multiplied by this thing here. F is a particular function in this case. It's known as the transition function, the UTD transition function. And the transition function itself has as an argument the product of things, k, which is the wave number. This function here, a plus or a minus, which again depends on phi sub I and phi sub d. And then these parameters L super I, L super Rn, and L super R naught, which are referred to as distance parameters. So I'll explain each one of these in turn. Now this is a good point to kind of stop and remind you of something here. This expression is quite complex, but it really is pretty simple to implement. The issue is simply that you have to understand the definitions of all these parameters. And that's what we're going to spend the next few slides doing. Once you understand geometrically what these parameters are, this turns out to be quite simple to implement. The second thing I should say here is that As far as you're concerned, this expression is just coming out of the blue. I will assure you that this is actually a mathematically rigorous equation, and it comes from a particular derivation. And you can get the overview of that derivation from this Quimjian and Pathak paper cited at the bottom of the slide. The math is pretty far beyond what we can do in this course. So I'm simply presenting the result to you here, and I'm showing you that it makes sense. This a parameter, this a function, a plus and a minus, it takes as an argument a angle, and the whole thing works like this. A is 2 times cosine squared of this argument. The argument psi here is the argument which appears as the argument of the a function. N is related to the wedge angle, as I've already explained. And then we have this parameter big N, which either has a superscript of plus or minus. This parameter is the integer, either -1, 0, or +1, that most nearly satisfies this equation. 2 pi little n, big N, minus psi, the argument of the a function, equals plus or minus pi. The L parameters, again, these are distance parameters. I'll define these in slides to follow here. And then, as I said before, f is the transition function. Its argument is the product of the wave number, a distance parameter, and the a function. Okay, so there are 3 UTD distance parameters. The first one, L super I, is defined as shown here. S super D, of course, is the distance from the point of diffraction to the field point. Beta naught, we've already explained, that's the angle between the incident ray, or the diffracted ray, and the edge tangent. So that we've already described. What's new here are these parameters rho super I sub 1, 2. These are the principal radii of curvature of the incident wavefront. So what you do is you consider the incident wavefront, you identify the maximum and minimum radius of curvature of that wavefront, and then those two values are rho super I sub 1 and rho super I sub 2. Now rho sub E super I is the radius of curvature of the incident wavefront in the plane of incidence. Now note, these are the principal radii of curvature up here. This is also radius of curvature, but in a different plane. That is the plane of incidence, the plane that contains both the direction of incidence and the edge tangent. So we've got 3 radii of curvature of the incident wavefront to consider here. Now, at first glance, that may seem overwhelming, but in fact, it usually gets much simpler than that. For example, if the incident wavefront is spherical, then all 3 of these radii of curvature are simply equal to the distance between the source and the diffraction point, because a spherical wavefront has equal radii of curvature no matter what plane you consider. In that case, the L parameter for instance, L super I, is simply given as this thing, S super I, S super D over the total path length, S super I plus S super D, sine squared beta naught. So in the case where the incident wavefront is spherical, this expression gets very simple. It's also simple in the case where the incident wavefront is planar. In that case, all the relevant radii of curvature are infinite, and the L parameter becomes simply S super D times sine squared beta naught. So you can see here that even though this is quite complicated up here, for most practical cases, we usually have planar or spherical waves incident, or we often have those, and so those L parameters are quite simple. The next distance parameter is L super R naught. Now you might infer from the superscript R that this has to do with reflection, and it does. In fact, we have a very similar looking expression here for this L parameter, and we have a whole bunch of rho parameters, and rhos are always radii of curvature in this particular formulation. So what we have here is that rho super R naught sub 1, 2 are the principal radii of curvature of the wavefront reflected from the zero face. Right? So what you do is you determine the wavefront that is reflected, and that's in the geometrical optics sense, from the O face, or the zero face, and then you determine the principal, that is the maximum minimum radii of curvature. And then, as you might anticipate at this point, the subscript E indicates the same measurement, but now in the plane of diffraction. That is the plane which contains the direction of diffraction and the edge tangent. Now, something useful happens here. If the surface radius of curvature is large at the point of diffraction, and you have an incident wavefront which is spherical, then you can see right away that the 3 radii of curvature that go up here are all equal to S super I. That's because reflection from a planar surface does not change the wavefront curvature, right? If you have a spherical wave incident on a planar surface, then you get a spherical reflected wave. And then L super R naught just becomes this expression. Similarly, something simple happens here for the planar case. Again, if we have an incident wavefront which is planar, and it's incident on a planar surface, then the reflected wavefront curvature is also infinite. And so here is a simple form of the distance parameter. So again, you can see the distance parameters are quite simple in cases which we commonly encounter. Not always, but often. Then finally, we have the distance parameter L super R n. Now, this is just like L super R naught. The only difference is now we're talking about reflection from the n face. So everything I just said applies again, except now we're talking about reflection from the n face of the wedge. Just as in that previous case, we get simplification for the spherical incident wavefront case and the planar incident wavefront case if we can assume that the surface radius of curvature is large at the point of diffraction. So we have these 2 L parameters, these 2 distance parameters associated with reflection. These are the 2 that are associated with reflection from the zero face and from the n face. Now, what happens if the surface radius of curvature is not large at the point of diffraction? In that case, the reflected wavefront curvatures cannot be assumed to be equal to the incident wavefront curvatures, in which case it gets kind of complicated. These are the relevant expressions. Now, on one hand, these are kind of ugly. On the other hand, this is straightforward geometrical optics reflection. So computing these wavefront curvatures is simply applying geometrical optics to the zero and n faces independently, and then computing these wavefront curvatures. So you can refer to a previous lecture where I talked about geometrical optics reflection for a refresher on how to use these equations. And again, you only really need these if the surface curvature is not large at the point of diffraction. Oh, and by the way, what do I mean by not large? Well, that's relative to a wavelength. Right? So if the wavelength is, so if the radius of curvature is 100 times the wavelength, that's large. Okay, the transition function, this f function here, it is defined as shown here. It is 2 times j times the square root of the argument, e times e raised to the j times the argument, and then this integral. This integral you take as endpoints the square root of the argument and you integrate off to infinity. I'll tell you right away that there is no closed form solution to that integral. You must do it numerically. Now, in the year 2016, this is a no-brainer. You can do this integral very, very quickly, regardless of what the problem entails. In 1974, that integration was tedious. So there was considerable work invested in coming up with a quick way to estimate this integral with sufficient accuracy for problems of practical interest. So I'm going to show you that approximation. Do you need to use it? Not really. It's a convenient way to do it. It's kind of a standard way to do it. But if you'd rather do a numerical integration here, that's really no problem. It goes quite quickly. If, on the other hand, you'd like to see these approximate expressions, those are kind of nice too. So I'm going to show them to you. The small argument approximation to the transition function goes like this. It works for values of the argument that go from 0 to 0.3, and it's a simple closed form expression, simply a 3-term expression. There's a large argument expression, which works for arguments which are greater than 5.5, and is this 5-term series here. Again, very simple closed form expression. That leaves a gap between 0.3 and 5.5. In that range, the only reasonable way to do it is to interpolate. To interpolate, what you do is you use this generating function in which you find a value of x sub n for which the transition function is already known, and then you extrapolate using these coefficients a sub n. And here's the table. So, for example, for x equals 0.3, we know what the transition function's value is, and then we can extrapolate to a new value using this factor a sub n. And for arguments less than 0, we simply note this property of the transition function, it's conjugate symmetric. 3 parts of this approximate form of the UTD transition function, or you can just do the numerical integration, whatever suits you. Here's what it looks like. So this is a plot of the magnitude of the transition function. It's complex valued, so I'm showing just the magnitude here, as x goes from 0.001 to 10. And in general, it increases. And the phase goes from about 45 degrees to a very small number. So that's what the UTD transition function looks like.